on to the more scientific part of the program. We have Soliton stars as holographic confined Fermi liquids. Thank you very much.
Thank you. Yeah. Firstly, I'd like to thank the organizers of this wonderful conference to invite me here and giving me the opportunity to talk. So I'll be talking about some holographic realizations of confined Fermi liquids. And this talk is based on a work that I did with Professor Takayanagi, Noriaki, and Tomonori. So Fermi surfaces have been studied in several holographic contexts. Pointer?
There's a nice big one there. Here.
Oh, yeah. Sorry. Yeah. Yeah, Fermi surfaces have been studied in several holographic contexts. The first one being studied in detail is that of extremal black holes. So people have studied probe fermions in extremal black hole backgrounds, and these extremal black holes, as is well known, has a ADS2 geometry in the IR, and it is found that that in this ADS2 geometry the fermion 2-point functions have cuts instead of poles, and therefore the behavior, the corresponding behavior of of the boundary theory in this context is that of a non-Fermi liquid rather than a Fermi liquid. And so in order to focus on Fermi liquids, people constructed electron stars more recently, and these electron stars in the IR have a Lifshitz kind of geometry. And even in this case, in the case of electron stars, the excitations, the low frequency excitations in the IR region, in the IR Lifshitz geometry, are dominated by gluon-like excitations, and they don't have typical Fermi surface behavior. If you compute something like entanglement entropy or specific heat, they don't exactly capture the Fermi surface physics in a very essential way. So realistic condensed matter system, on the other hand, have confined Fermi surfaces, in the sense that the gapless excitations are only about the Fermi surface, and they are uncharged under the gauge group. And there was one attempt to actually holographically capture this phenomena, where there was a hard wall geometry. The ADS space was cut off into by a hard wall, and then probe fermions were studied in this geometry. But as you start taking into back reaction, then these geometries might get severely modified, and as a matter of fact, this hard wall may in fact become absent as you start taking into account a back reaction. So in order to modify this defect, we actually constructed a full back reacted solution of a fermion system in the so-called ADS Soliton geometry, which is actually capped off in the IR. Which has very similar features like the hard wall geometry, but here we could consider the fermions in a particular fluid approximation, in a Thomas Fermi approximation. We considered these fermions, and we considered the back reaction of these fermions, and constructed this full back reacted geometry, which has a cutoff in the IR. Yes.
I would say that that's a property of Fermi liquid theory, not of realistic condensed matter systems. Anything that's not a Fermi liquid theory might have this gapless degrees of freedom that you're worried about. When you have a Fermi surface coupled to a gauge field, for example, and
yes,
you can get that. So it's just a property of Fermi liquid theory that you expect not to have this other degrees of freedom.
That's right. So what we intend to do is to capture the Fermi liquid theory in a holographic context, where the excitations are precisely the low energy excitations are precisely the ones about the Fermi surface.
That's right. I just wanted to point out that all these interesting systems that are not Fermi liquids probably do have all these other degrees of freedom. That's what makes them interesting.
Okay, if you're referring to something like non-Fermi liquids, so-called non-Fermi liquids, then of course they are studied. They are somewhat captured by these the extremal black holes and the excitations thereof. But the intention here is to before going into non-Fermi liquids, and before actually studying a phenomenon which is even very hard to capture from a boundary theory point of view. we intend to, first holographically capture
That's fine.
a very well-known.
I was just
Right.
making for a realistic condensed matter system.
Okay. So, by this what I mean is, realistic non-exotic condensed matter system, if you like. Okay. So, okay, now after constructing this geometry, which I'll explain to you in detail, we consider probe fermions in this geometry and look at the 2-point function of these probe fermions. And through that analysis, we find a large number of very sharp Fermi surfaces in this geometry. And we also study the phase space of all the known zero so these solutions that we will construct are zero temperature solutions in just like the ones like the electron stars, and we will finally study the phase space of all these three zero temperature solutions and find interesting phase transitions. So that's a brief introduction to what I'm going to talk about. Here's a brief outline of my talk. Firstly, I'll talk about the general setup, where I'll set up the equations that I intend to solve and study. Then I'll include a brief description of the electron star. I should emphasize that the electron star was originally constructed in 4 dimensions, and but we wanted to compare the electron star with our Soliton star, which we did in 5 dimensions. So here is a slight generalization of previous work. We construct the electron star in 4 dimensions, and I would include a brief discussion of that. Also, I would like to emphasize on points which become relevant when I start comparing it with the Soliton star. And then I'll talk briefly about the construction of the Soliton star in a perturbative analysis. I'll tell you what the parameters of the perturbation theory are, and then I will tell you about the numerical solution of the Soliton star. In order to move away from perturbation theory, we had to construct numerical solutions, and these numerical solutions match very well with the perturbative solutions in the regime where they are expected to. And after constructing the Soliton stars numerically, I would compare them with the electron star and the zero temperature Eisner-Ostrom black hole, the extremal black hole, and present to you the phase space of these existing solutions. And finally, I'll discuss the probe fermion analysis, and after that, I'll conclude with some outlook. Okay. So the system that we consider is the Maxwell-Einstein system, which is coupled to a charged fermion. In fact, it can couple to many charged fermions, and the fermions would be treated in a fluid approximation, in the so-called Thomas Fermi approximation. And the equation of motion that we intend to solve is simply the Einstein equation, where you can see this is the cosmological constant piece, and this is the stress tensor because of the Maxwell field. And this is the stress tensor coming from the fermionic part, and we also have the Maxwell equation, which is sourced by a current due to the fermion. Now, in our analysis, we assume the fermions to be in a fluid approximation, and therefore the stress tensor of the fermion is assumed to be given by the perfect fluid form, where P is the pressure and rho is the energy density, and similarly the current is given has the perfect fluid form without considering higher derivative corrections. This is the charge density of the fermions, and in particular, I should say that there are these curvature scales and the Newton's constant and the charge of the fermion that are there, but we work in a particular scaling limit where we rescale our original parameters, the pressure, the energy density, in this following way. And so this beta controls the in some sense this is the you can think of this beta as the number of fermions that are there in the system, but you can so this gets I mean in the scaling limit that we considered, beta gets rescaled in this following way, and this m is the mass of the fermion, which will become explicit in the next slide. So in this limit, what happens? These the gravitational constant, the Newton constant, the charge of the fermion, and the gravitational scale drops out of these equations, as you can see here, and therefore we can set them to 1 and do our calculations, and it is very easy to restore them at the end if you want to. And so we will perform this rescaling and work with these parameters instead of these fields instead of the original ones. And I should also point out something here, that I mean, if you want to get rid of these parameters from the Lagrangian, we need to scale the gauge field in this following way. And if you I mean, if you think of let's say n equal to 4 Yang-Mills, I mean the corresponding thing for n equal to 4 Yang-Mills, then this number goes as some positive power of n, which implies that the charge as well as the chemical potential that we'll talk about in the system is very large in our context. So also I should point out that this parameter beta and the parameter m are the two Lagrangian parameters that we have in our system, and we shall actually try and look at solutions for various values of beta and m. We won't confine to any particular value. So these are the equations. Now we want to solve these equations with a given metric ansatz, and this will be the general metric ansatz for our solution, where for our Soliton stars, the general rotational symmetry between this theta and the xy directions would be broken, and this will be captured by this non-trivial function. However, for the electron star, this k of z is simply 1 by z square, and in that case rotational symmetry between theta and xy coordinates would be restored. Also, this theta, I should emphasize, is actually a circle which you can think of as some kind of a short circle in the boundary, and so the value of this function k, for instance, at the boundary would give you the radius of the theta circle in case of the Soliton star. I will describe in detail how this goes about. And also we only consider one time component of the gauge field, which is non-zero in this case, and that is denoted by h of z. Okay, now so as we had considered the fermions to be a fluid, and that to a perfect fluid, the perfect fluid equations are actually solved by this configuration. So since we were interested in a zero temperature configuration, we have set the temperature to 0, and also we don't consider any rotations, so this for velocity is simply given by this expression. The chemical potential is non-trivial. This h of z, let me remind you, is the time component of the gauge field, and this is the time component of the metric, the function f. And so once we assume this form of the fluid variables, then the fluid equations are automatically solved. In fact, this is one solution to the fluid equations, and now the energy density and the charge density for the fermions are so the fact that we are dealing with fermions are captured by the density of state, which enters the expression of the energy density and charge density in this way. So S of E. Yes.
H was 0 would just mean there was no gauge field.
It was the time component of the gauge field.
So why does rho have to be 0 if H is 0?
Why does, sorry, so it's the time component of the gauge field.
So if rho is 0.
So now this integration is from m to mu, where this chemical potential is given by this expression, and so whenever
H is 0, mu is 0.
When mu is equal to m, H is 0.
Mu is
Rho is 0. When mu is equal to m, rho is 0.
So, Okay, well, what happens if H is actually 0?
Okay, so so if this I mean this whole geometry is non-trivial because of the presence of fermions which are charged. Okay, and if you take this fermions and put them in whatever array for the electron star or the soliton star, then these will be some charged objects, and then H will not be 0. It's basically it gives rise to the electric field because of the charge.
Neutral configuration.
So we are considering the fermions to be charged here, and therefore this charge density is non-trivial. So the fermions are charged.
I think what Andy is saying is that there is a limit. You can have a limit where you don't have the fluid, where you just get back to the normal thing where you don't have the charge outside. And that limit seems a bit strange, because that would seem to be the H going to 0, not the mu going to M limit. But that's what you're after, right? I mean,
So
I'm just trying to take some limits of this expression. Okay.
the mu going to M.
let's say
If
if
we have a neutral path of fermions, or it's always charged?
it's always charged. I mean, at least in the context that I am considering, it is charged.
So there's no anti-fermions?
There are no anti-fermions, right?
You're feeding the Fermi energy up to some point. It doesn't matter what's at the bottom. You just feel the Fermi C up to some point. And the reason
Here, there should be a limit where you don't have any. I mean, where you just get
Yeah,
the
the
rest
chemical
of it.
It's
potential-
not the fermion number density, it's the charge density, right?
it's the same thing in this particular setup.
Oh, it is?
Yeah. And the reason why it's the mass that sets the bound is because if your chemical potential is not enough to get to the mass, you cannot create any fermions. So the
No,
mass is
I
really
do.
the zero of the chemical potential.
No, they're not. I mean, it's a relativistic theory, fermion. Density and charge density are not the same.
The only charge source he has in the bulk are fermions.
There is no density of states below M, so
Yeah.
S of E is 0 below M, so you could as well put the lower limit to 0. S of E is the dispersion relation for the fermions, right? That's 0 for E less than M.
Yeah. So S of E, as you said, is the density of states, and I mean, if you consider in our set of approximations, the mass of the fermion is such that the Compton wavelength, which is the inverse mass, is small compared to the curvature scales, and therefore the fermion doesn't see the curvature of space. So it's legitimate to consider the density of states, which is a density of states which is that of 5D flat space, as you could see, as you could obtain by considering momentum shell in 5D flat space. And so if you so this is the expression for the density of states, and so if this is the density of states, then the energy density is given by the integration of energy times the density of states from the mass of the fermion to the chemical potential, and therefore for this construction it is important that the chemical potential is greater than the mass of the fermion. And as soon as the mass and the chemical potential become same, so you set both the energy density and the charge density goes to 0, and it remains 0 if it is of other sign. I mean, there doesn't exist any fermion where I mean, there is no non-trivial fermion density if the chemical potential is less than the mass of the fermion. And also we need for solving the equations, we also need the pressure, which is given by the Gibbs-Duhem relation. It is related to the charge density and the energy density. And note that there is no S times T term here because we are looking at zero temperature solutions. Yeah. So before describing the electron stars, let me just pause a while to describe one geometry, which is the Lefschetz geometry. And so in our ansatz, if we take the function k of z to be 1 by z square, then there exists a solution of the system of equations I showed you, and this is the so-called Lifshitz solution. And in this solution, the space and the time coordinates scale differently, and it's a scaling solution, and it's an exact solution of the Einstein equation. And these parameters alpha and GL are exactly determined in terms of the Lagrangian parameters, which is m and beta. And so if you and actually, you know, the relation of GL and alpha with m and beta is quite complicated. I haven't written them down, but the behavior of alpha with beta for various values of mass is shown here. And in particular, note that for beta equal to 0, the alpha is basically infinite, and if you take that limit in this geometry, you will get the ADS2 kind of geometry. Also another point is that, you know, as you take m towards 1, and you know, even then alpha diverges, and we get this ADS2 geometry. And in particular, if you want as you take m to 1, then the chemical potential, which is this divided by square root of f, also goes to 1. And in this case, the inequality that I showed you for the existence of this kind of solution is saturated, and therefore this m equals to 1 is an upper bound. I mean, in the convention that I am working, m equals to 1 is the upper bound for the mass of the fermion for these solutions to exist. This
Axes on the graph.
So this is alpha and this is beta. Alpha is this scaling, this dynamical scaling, and beta is the Lagrangian parameter, which you can think of as roughly the number of fermions rescaled. Okay, so now the electron star is another solution of the same system in the same symmetry sector, which actually reduces to this IR Lifshitz geometry that I just showed you. And for constructing the electron star, we actually perturb away from this IR Lifshitz geometry and numerically construct the solution in rest of the space. And we find that there occurs a point where the chemical potential basically becomes equal to that of the mass of the fermion, and it is at that point that we have the radius of the star, and I mean none of the fermion fluid can exist beyond that point. And and also, as we have seen, that for this electron star to exist, since this electron star has a IR Lifshitz geometry, the mass of the fermion must be must be less than 1, otherwise this solution will not exist. And so the inequality would be saturated at the radius of the electron star, and the solution outside the radius would be a vacuum solution of the Einstein-Maxwell system. And in this particular symmetry sector, I think there is a unique solution, which is the Rn black hole solution. So we'll take the Rn black hole solution outside and patch it with this electron star solution at the position of the horizon, and we will do a first derivative match. So if we do that, so here is a very brief procedure. So this was the initial Lifshitz geometry, and we perturbed away from this geometry, and this was used to put in the initial condition for the numerics. And so we found the radius of the star here, and by this condition, and then patched it up with this Reisner-Armstrong solution outside. And so in summary, the form of the electron star is as follows. So you have a Lifshitz geometry here, and there is a radius where the chemical potential equals to the mass, And so here we perform a perturbation theory away from the Lifshitz geometry, and in this region of space basically we solve the equations numerically. And outside here is simply the Reisman-Osborn black hole solution. Okay, so here are the form of the functions. These are the various. This is the time component of the metric. This is the ZZ component of the metric. This is the form of the gauge field. Here I have also plotted the chemical potential just to give you an idea that if you start from the deep IR, then this is the red line is the perturbation theory line, and it sort of breaks down as you approach the z equal to 1 point. And from there, this is the region for which you require the numerical solution. If you continue the numerical solution, you get a point where the chemical potential actually comes below the mass, which is taken to be 1/3 here. And so this gives us the radius of the star, and outside this you have the Reisman. You know the solution exactly in this particular case, and you sort of do a patch here at the radius of the star. Now, so let me quickly move on to the Soliton star geometry. For the Soliton star, this function k of z is very non-trivial, and so first to construct the Soliton star, we formally treat beta as a perturbation parameter and slowly develop the pile of fermions in the bulk. And the perturbation that we do is about this ADS Soliton geometry, where you can see that this function k of z has a 0 at k equal to at z equal to 1. So which means that this theta circle gradually caps up to 0 at this point, and this is the IR hard wall kind of this feature captures the IR hard wall geometry. And also we don't want any singularities at that point, so the g of z function also must have this form. Now, and so this is basically the Soliton geometry, where you have this circle in the boundary and that sort of smoothly caps off in the bulk. And here you now put in some amount of this matter, and you develop the point where again the chemical potential is equal to the mass at some point, and then you have this is the radius of the star. Now outside the radius we have a different solution, and we have to different solution compared to Rn ADS solution, and we actually have to calculate what that solution is. So if we do this perturbation theory, we could construct this solution outside as a in terms order by order in beta, and also we sort of later when we do the numerical solution, we numerically construct this part outside. Now this solution outside has a feature that it asymptotes to the ADS Soliton kind of geometry, this kind of geometry, and we maintain that boundary condition. So for the numerical solution, we start from this tip of the Soliton and construct a series solution initially, just to provide the initial condition for our numerics. And so this is of this form again, and as you can see, there is we maintain the fact that there is a 0 of this k of z at the tip, and Now once we feed in the initial values into the numerical solution, it is very easy to take this solution forward, and the thing that I should point out here, this Soliton star has crucially has one extra parameter compared to the electron star or the extremal black hole, which are basically parameterless in this planar limit that we are considering. And we can take this extra parameter to be anything, but we find it convenient to take this value of h naught, the so which turns out to be the value of the chemical potential at the tip of the soliton star to be this additional parameter that parameterizes our solution. So this is a parameter of the solution, contrary to beta and m, which are Lagrangian parameters. And of course, for the solution to exist, we should at least initially have the value of the chemical potential at the tip must be greater than m, and then it monotonically decreases at some point and hits m, and the point at which it becomes equal to m forms the radius of the star. And it also turns out that the h naught must be greater than m, but it also has a upper bound which turns out that at some value of h naught the solution actually starts developing singularities. And it would have been apparent, so the expressions for this f and g and g minus 1, these are very complicated, I haven't written them down, but you would see that these solutions would start blowing up at, these numbers would start blowing up at some value of this h naught, and we have to be below that upper bound so as to write down a non-singular solution. So therefore h naught is bounded from below by m, and it also has an upper bound for the solution to exist. And so these are the form of the solution. I don't know if the line in between is visible. So the line in between is a numerical solution which is done for a very small value of beta, and the broad and the thick lines over it are the perturbative solution. You can see how very well it matches with perturbation theory for small values of beta, and there are of course deviations if you consider large values of beta. This straight line is basically the radius of the star, and we have first derivative patch at the radius. Okay.
What's happening to g of z in that figure?
What's
the g of z?
There is no, so this z equal to 1 is basically the tip of the star, right? And there is a, if you remember for having regular conditions, the g of z function has to blow up at the tip of the star. So it's that blow up that you are seeing. Basically, k of z has a 0 near the tip, and g of z has a, it's basically the coordinates that I'm working in. So this is that blow up that you see. Okay, now now once we have constructed our full solution, the asymptotic form of the solution has this form, and one could through a proper fitting analysis read off all these values from the solution, these asymptotic values from the solution. And so now since we intend to compare our various thermodynamic quantities of our solution with that of the electron star, we need to get rid of a scale transformation, scaling invariance that is present in these solutions. And we fix that scale invariance to set the asymptotic theta circle to that of unit radius, and so that we compare all the soliton star as well as electron star as well as the extremal black hole with a unit radius circle at infinity. And to do that, we find that the scale invariant parameters that our solution have are this energy. So this Tt is the time component of the boundary stress tensor. This is the thing that corresponds to energy. For temperature equal to 0 solutions, this is also the free energy of our solution. And we also have the charge, which should be rescaled in this way to make it dimensionless. And also for technical convenience, it is useful to consider basically a ratio between the energy and charge. And this ratio gets fixed to some single number for the electron star as well as the extremal black hole, as I will show you. So for the electron, for the extremal Reisman-Ostrom black hole, this ratio turns out to be 81. And for the electron star, you can compute these ratios. using the external Reisner-Nordstrom kind of solution. And these ratio have this following form. So these are various graphs. These are various graphs for various values of m. The value of m approaches 1 as we move up, and this is the plot with respect to beta. So as you can see, for beta equal to 0 as well as for m which is very close to 1, this ratio approaches very closely to the value 81, which is the which is the extremal Reisner-Nordstrom value. And so this is consistent with the fact that I noted earlier that for these two limits the geometry actually become ADS2 in the IR. I mean the Lifshitz geometry actually becomes ADS2 kind of geometry. And also I should I should emphasize one point, that for all other values the electron star ratio, which you can think of as the energy at a given value of charge, is below that of the black hole value, and therefore the electron star seems to be wherever it exists seems to be a more stable solution compared to the black hole. Also, before doing the comparison with the Soliton stars, I should mention that we also looked at thermodynamic stability of these configurations. And so if this bound gets violated, then it is expected that there would be some sort of clumping of charge, and we would be in order to see those solutions exactly, we have to look at solutions which are outside the symmetry sector that we are analyzing. And however, by doing this thermodynamic analysis, we do indeed find that there are certain thermodynamic instabilities in this system for certain values of parameters, as I'll show you. And it would be interesting if these thermodynamic instabilities are accompanied by certain dynamical instabilities, and we are led to completely new sector of a solution where there is some clumped up charge in various regions of space. Yeah. So here's then, sorry, this diagram is, I'll show you a schematic of this diagram in a while. So this is the plot of ratio versus the charge for various various values of soliton stars and the electron stars. The electron stars, as you can imagine, is a straight line because this ratio is constant.
I don't think anyone can see.
Okay, let me show you a schematic of this. So here is a schematic of this. So this is a plot of this ratio versus the charge of our solution, and this red line is the electron star line, and this line always stays below the black hole line wherever we have. I have shown this result before. Now it so turns out that in certain region, again I will show you this region in the next slide. In certain region, basically there are three possibilities. In certain region, the soliton star always stays below the electron star, and it, for large charges, it actually asymptotically approaches the electron star. In fact, we found that the solution, the soliton star solution in the IR sort of develops a region which is very much similar to the electron star which is very similar to the Lifshitz solution in the IR geometry. And so in certain cases there is a clear indication that the soliton star crosses the electron star or the black hole line. And so here one would expect a sort of first order phase transition between the soliton star and the black hole, and the instability is the thermodynamic instability is indicated at some point which is above the electron star or the black hole. And there is yet another case where there are cases where the soliton star terminates even before reaching the electron star or the black hole line. This endpoint corresponding to the upper bound of H naught that I told you about. And however, in these cases it is found that wherever such a thing happened, it was found that there is an instability which is thermodynamic instability which occurred much before that. So expectedly some other solution takes over at this point. And there were certain cases where although the soliton star crossed the black hole line, there was some thermodynamic instability below that. So if I show you the whole phase space of beta and m. This is the rough plot. We have analyzed the points that are shown by dots and triangles. So this is the region which corresponds to the case 1 here, where the soliton star is always the most stable configuration. And here is a region where we always find that there exists a transition between the soliton star and the black hole. And this is the region where there is a thermodynamic instability which occurs before the soliton star crosses the black hole line or the electron star line. So this is the main result of our analysis of the soliton star, and then we quickly move on to the pro-fermion analysis, where we actually consider our soliton star geometry and put in fermions and solve the Dirac equation in the background. However, we can't solve this Dirac equation exactly. So we do something like a WKB approximation. We consider large mass and charge, and we also scale the frequency and the momentum in this way. However, I should point out that there's a momentum along the theta direction, and in the scaling limit we haven't scaled this momentum, which effectively got rid of this p from the equation. And this we justify by saying that we are basically interested in this 2 plus 1 dimensional physics, and so if in that case I mean it is sort of legitimate to look at this particular scaling. And so the Schrodinger equation then has this effective potential, which is given by this form, and these functions h of z and f of z are only known numerically. So one thing you can note here is that in the limit where the frequency and the momentum are set to 0, this potential has a 0 right just at the point of the at the point where there is the radius of the star, because h of z by root z was the chemical potential, and this is the point where it has a 0. So we had plotted this potential for various values of momentum and various values of the parameters using the numerical solution that we have, and in most cases that we find that so this is the zero momentum potential, and the momentum increases as we go higher. So in most cases we find that if there is a turning point in this potential, there is one single turning point in this potential. And for example, for the line at the bottom, the point where it crosses 0 is the radius of the star, and it's sort of corrected for higher and higher values of momentum. And we can conclude that there's a single zero of or a single turning point for this effective Schrodinger potential that we have. And if you do a WKB analysis of that, you will find that so if this z star is that particular value of turning point, and if you define your x and y quantities as with potential in this way, then you will find that there are.
Sorry, can you go back to the potentials? Do they just fall in?
Yeah, I mean this is the shape. This goes to I mean,
how could you have that? I mean, that's usually the horizon. So
no, this is the IR.
That's what I'm saying. So
Yeah.
in the electron stars, having that potential fall in, it's just representing the Lifshitz horizon, that you can have quasi-normal modes of things falling behind the horizon, but your geometry is capped.
But here that's the point. So here we put the boundary condition that the fermions at the tip at z equal to 1 vanishes, because we have antiperiodic boundary conditions on the circle, and that circle sinks to 0 at z equal to 1. So the fermion wave function must vanish at this tip, and with that you can do the WKB analysis and find that there are sharp poles. There are no imaginary part to that.
Oh, okay.
So this is the result that we have. That typically if you look at this answer in the case of electron stars, you will find an imaginary piece here, which indicates the fact that the fermions can fall through the Lifshitz, or I mean the z equal to 0 point. But here
is it the potential doesn't fall fast enough, so you can have stable modes? trapped in that.
Yeah, you can say that. You can say that. In the effect, in the so this Schrodinger equation is an effective Schrodinger equation in some sense. So I mean, so this potential is the so this potential is the effective potential that this fermion sees.
So the spectrum is bounded below.
The spectrum is bounded below, right? Okay. And okay, so basically we find very large number of so these are the poles that we observe in the spectrum.
So what is y hat and x hat?
So it's defined in here. Okay. Yeah, actually, I should have put a hat here. Okay. No, actually, there's a distinction between x hat and y hat is basically, y is this function which is defined from z star, which is the turning point to this to a lower value of z. So here, if you like, in this potential, so this is the value of z star. So x is defined in this region where the potential is positive, and y is defined in this region where the potential is negative, and y hat is precisely the value when you take the value of z to be this IR point. So y hat is a number instead of a function, and that number is basically equal to n times pi, and you can put in zero frequency in this potential and calculate the Fermi surfaces by computing the zero frequency momentum values for this pole. Yeah. So as I have emphasized that this is contrary to electron stars, where you have a basically imaginary piece to this point, and so basically we have very sharp Fermi surfaces and many Fermi surfaces, which is sort of similar to a system which, if you have deconfined fermions in the large n limit in the adjoint representation. So if you have fermions in the adjoint representation, and you have a gauge field, and in the free limit in the deconfined phase, you would find such behavior. If you calculate the specific heat, for example, it will scale with n square. So from there you can conclude that this kind of large. All I'm trying to say by this analogy is this kind of large number of Fermi surfaces is not very uncommon in this gauge gravity duality, and it would correspond to several bound states.
Are there any low energy condensed matter systems that have adjoint fermions?
Not that I know of any. Yeah.
And what is the deep IR geometry that you said in your solution?
So the IR geometry is capped up at a particular value of z, which we took.
So that's just confined.
Yeah, it's confined.
Do you have a mechanism of moving away from the Thomas Fermi approximation in this system?
Well, for that you have to take into account back reaction of fermions, which is a very, if you really want to do the back reacted problem. So that's a quantum problem, hard problem. Yeah. Okay, so let me conclude here. So we had studied a holographic model of the confined Fermi liquid, and we did this by putting fermions in the ADS Soliton geometry. And so I should point out one very attractive feature of our solutions, which is also there, for instance, in the electron star, and this is the fact that it obeys Luttinger theorem, in the which is a way of saying that all the charge in our solution is carried by the fermions. There's no horizon which hides certain number of Fermi surfaces or some such thing, and so our solution is characterized by many sharp Fermi surfaces, and so also we found certain very interesting phase transition between the Soliton star and the electron star, and we also found indication of the existence of certain inhomogeneous phases or certain inhomogeneous solutions, which would be interesting to probe and see if they fit in and complete the phase diagram in that at that point that I showed you. Also, it would be interesting to understand other properties of Fermi surfaces through this mechanism. Like if we can see if we can capture the effect of anomalies. The question that how Fermi surfaces actually capture the effect of anomalies in the system if there is one present. And one way to do that would be to actually consider a Chern-Simons term in the bulk and modify the Maxwell equation that we wrote down and see the effect of the coefficient of that term in the position or in the Fermi surface physics that we explored. Yes.
Question. So if you go back to a previous slide,
Yeah.
in the last part you mentioned that there are these adjoint fermions, but
Yeah.
the probe fermion that you put in the bulk is actually not charged under the gauge group, right?
Yeah. I mean, this was a completely different. I mean, it had got firstly it was in a deconfined phase. I mean, this is just a completely different analogy just to show you the fact that it will not be. It's the fact that there are a large number of Fermi surfaces is not a very unknown feature in a large N theory. Just to convince you.
Right, but what is in your system? What's the interpretation of these many Fermi surfaces? Because
Yeah, it would have similar interpretation. Like it would correspond to certain bound states that you can form out of effective way. But yeah, I mean it doesn't have a very direct interpretation in terms of.
But it's not these adjoint fermions.
It's not the adjoint fermions. It's some effective thing. Yes.
In this holographic framework, you should think of this gauge invariant fermion as traces of let's say psi with some bosonic operator.
Yeah.
So there is a vibrational mode between psi and the bosonic excitation, and these are all different bound states. Of
I mean,
this
I was just
excitation.
confused by the comment about the adjoint.
Yeah, I agree.
Yeah, please.
So why do you call it a Fermi liquid? I mean, you say that the poles don't have an imaginary part at all, so Fermi liquid it would have omega squared.
We would have dissipation. That's what you're saying.
If you include 4 fermion interactions, you probably get that.
Yeah. So
So
this
the
is.
imaginary part come from the first irrelevant correction to the field theory.
Also, how does the large N counting work for Luttinger's theorem?
Yeah, so this is something, so this is something which so if you consider this, let me go back to actually I'm done with my talk, so if you,
So you say you have a lot of Fermi surfaces, but in terms of N, how many? The N.
no, we cannot characterize that because we're working in a gravity approximation which is strictly large N. So, I mean, all we can say there, I mean, so these are the Fermi surfaces are characterized by this integers N, which has, sort of, so for every value of this integer N, you get a, position of a Fermi surface if you solve this equation. So in that sense, it's very large, and so you cannot extract the power of N from this counting because it's taken to be like infinity for this gravity calculation.
But you said Luttinger's theorem was satisfied, and the charge density is order N squared. Then the sum
Charge density is not exactly order N squared in this particular thing that we are taking. It's N to the some positive power. I think it's N to some 2/3 or something. Yeah, it's some positive power. Yes.
But then you're saying that the volume of each Fermi surface is some power of N, and then I sum up some number of them.
Yes.
And it reproduces the same power of N.
Yes. I mean,
I haven't seen that done anywhere explicitly.
So basically, okay, in this holographic setup, the statement of Luttinger theorem becomes a statement of Gauss law, basically. Okay, so in case of there's a paper by I think Professor Sachdev where they actually explicitly write down the correction to Luttinger theorem if there is a IR point. So and you can take that expression and evaluate that expression for the case of our IR tip, and that evaluates to 0. So I mean, so Luttinger theorem is valid in that sense that, I mean, if you follow their analysis and evaluate that additional term, it evaluates to 0. So there is no correction to Luttinger theorem as such. Also, you can see this here very clearly because all the charges are carried by the fermions that are present in the system. There's no charged horizon or something like that which carries additional charge. So it's sort of.
Just I'm not that aware of these theta directions in the bulk. So is theta a direction of the boundary theory or not?
It's the direction of the boundary theory which sort of caps off in the bulk in this fashion.
Okay.
But you can think about having compactified that direction, and the rest of the directions that are 2 plus 1 dimensional, those are flat directions.
Right. So isn't that like an so it's not modeling an actual condensed matter system, because usually you think of all your space and time directions to be non-compact that way, right?
Yeah, but you can think of this as a 2 plus 1 dimensional condensed matter system where everything is non-compact, and you just have So it's actually a higher dimensional system where you have compactified and looking at the physics at the low energy physics of 2 plus 1 dimensional system.
Okay, so effectively, if I just look at the lowest levels of
Yeah.
fine mode,
If you look at modes which are not sensitive to this circle, then it would be like effectively 2 plus 1.
Any further questions? Speaker.